Welcome to discussion 29. In today's discussion, we'll focus on section 5.3 on the fundamental theorem of calculus. And in this video, we will do some FTC part 1 quick examples. So this is problem number 4 from worksheet 14, and I want to calculate the derivative of the following functions and simplify your answers if possible. So we will look at parts A, D, and E of this example. But before we do that, I just want to recall what the fundamental theorem of calculus part 1, or the FTC part 1, just to abbreviate it, I will write FTC 1, says. So if I take the derivative with respect to x of a definite integral where the bottom limit of integration is a constant, the upper limit of integration is the variable x, and then I have this function f of t. Okay, so the variable inside of the integral is different than the one up here. FTC part 1 says that this derivative of this area function ends up just being f of x. It ends up just being the function in the integral, but the t changes to an x. Okay, we can generalize this and take the derivative of a definite integral that goes from a constant to some stuff up here, f of t dt. And this involves the chain rule. This will involve the chain rule. Because now for the x that used to be in the upper limit of integration, we are sort of plugging in this inside function, the stuff. So the chain rule will give us that this derivative ends up being the derivative of the outside thing, the integral function, which using FTC part 1, I would typically write f of x, but the chain rule says don't write f of x, write f of, and then keep plugging that same stuff in, write f of stuff. But then do the chain rule step and multiply by the derivative of that stuff. So we'll use that when this upper limit of integration isn't just x, when it's something more complicated. Okay, so now I want to give you 4 minutes to try parts A, D, and E. So 4, 3, 2, 1, pause the video, pause it for 4 minutes to try those 3 problems. Alrighty, so hopefully you did that. Hopefully paused it and tried these for about 4 minutes. Let's talk about them. So for part A, to take this derivative, we are going to use FTC part 1. And it says that when we do this derivative, because this is just an integral from a constant to the variable x, what we'll get is we'll get this function that's in terms of t, but we just change the t's to x's. That's what FTC part 1 says happens. So we'll get x squared sine x. And the question said, well, simplify your answers if possible, and this is already fully simplified, so I'd leave it like this. Okay, and that's it. That was part A. All right, let's look at part D now. So in D, we have the integral from 3x to x to the third ln of t minus 1. So I noticed that with our integral, we have variables on the bottom limit of integration and the upper one, but we can only apply FTC part 1 when we're taking the derivative and we have a constant at the bottom and some stuff with the variable at the top, and we have f of t dt. But we can't do it when there's variables at the top and at the bottom. So I need some way to rewrite my integral. So there's going to be one constant and the other stuff is going to have a variable in terms of these limits of integration. So here's how we'll do that. I'm going to split this integral up into 2 pieces. One piece that goes from 3x to some number that we'll think about of our function, ln of t minus 1 dt, and then plus an integral that goes from whatever that number is, that this first upper limit of integration was, to x to the third of ln of t minus 1 dt. Okay, so in this box, we have to be putting the same number, because this is just one of our integral properties, that when we add 2 integrals like this, it'll end up being one integral that goes from 3x to x to the third. But the number that goes in here needs to be in the domain of that inside function. So this whole inside function, I'm just going to call this f of t. f of t. Okay. So usually I want to pick a simple number like 0, but if I plug in 0, I get ln of a -1, and that's undefined. I would need to plug in something maybe like 2. Because if I plug in 2, we'd get ln of 1, and that is defined. Okay, so now the second integral I'm going to be able to handle. I got a constant at the bottom and a thing with a variable at the top. And FTC part 1 tells me how to handle that. But the first integral, it doesn't look like that. I got variables at the bottom and a constant at the top. So I'm going to flip it, which puts a negative sign in front. Then we'll get 2 to 3x ln of t minus 1 dt plus that second integral from 2 to x to the third ln of t minus 1 dt. And now we're going to be ready to take this derivative. So this implies that my derivative, g prime of x, for this first function, what will happen is that negative will stay there. Then I'm going to take this stuff up here, the 3x, I'll plug it in, and I'll get ln of 3x minus 1. And then we multiply by the derivative of the stuff, which is 3. So this is the derivative of that 3x. Okay, and now we do the same type of thing for the next integral. So when we take the derivative, the x to the third will get plugged in, and I'll get ln of x to the third minus 1, and then I multiply by the derivative of x to the third, which is 3x squared. Okay, so I could just rewrite this a little bit, and we'll get g prime of x equals negative 3 ln of 3x minus 1 plus 3x squared ln of x to the third minus 1. And that is our answer. That is our derivative. All right, let's do one final part to this example. All right, we're going to do part E, where we have the integral of the same function, but now our limits of integration are 3 and e to the third. So I notice here that both of these have no variables in them. No variables in that 3, no variables in that e to the third. So this is just going to be some finite area. So this integral is going to be a constant number. So this integral is going to be a constant. It's not going to be in terms of a variable. So because we're taking the derivative, that means we are just taking the derivative of a constant. But the derivative of a constant is just 0. And that's my answer.